Okay, so hello and welcome to everyone who's joining our webinar today. It's great to see so many of you tuning in from all corners of the world today. Looking forward to learning a little bit about where you're all coming in from. So please say hello and tell us where you're from in the chat box. And feel free to ask any questions throughout the webinar about the content that we cover today. My name is James, and I am the course advisor for our Sustainable Electrical Power Systems Engineering program at the University of Manchester. And so it's my role to guide you through your initial inquiries and interest in the program, right through until you make your application and hopefully receive an offer for the program. I'm joined today by Dr. James Brooks, who is the program director for the Sustainable Electrical Power Systems Engineering online program. And he is going to be talking to you a little bit later in this webinar about the content of today's webinar, which is challenges of sustainability in power systems engineering. So James will talk about that in a minute, and then after that we'll talk a little bit about the Sustainable Electrical Power Systems Engineering program that we offer, and we'll also have opportunities for a Q&A at the end. And feel free to ask any questions in the chat box or the Q&A function, and we'll try to get to all of those. So I'll hand over to you now, James, if you'd like to introduce yourself.
Brilliant. Yeah, thanks very much. So yeah, confusingly, I'm also called James, but I'm the academic course director. So I'm responsible for the academic content of the MSc program as a whole. Originally, my kind of research area back in my PhD was quantifying the risks with renewable power generation. But more recently, I've sort of taken up this role of academic lead for pedagogy across all of science and engineering. So something like 8,000 students and 600 academics, something like that, trying to improve the quality of teaching. So I have this real interest in how do we design learning so that students get the most out of it. Hopefully that comes through in the material in the MSc that's put together. But there's obviously quite a large team that were involved, and we're quite lucky at Manchester to have a large team to put together the MSc with expertise in different areas. Okay, so let me move through the slides. So I wanted to sort of narrow down the topic. Sorry, I'm having a bit of problems with the slides there. There we go. Rather than just looking at sustainability broadly, I wanted to just narrow it down to one specific question. What if every UK household has a solar panel? And I'm not going to be as rigorous or as authoritative as I would be in the MSc. I just want to touch on some ideas and some areas to give you a feel of the challenges. And then maybe at the end, I'll talk about how it links back to the content that we actually teach in the MSc. So the reason I chose this question was sort of because of these two graphs. On the right-hand side, you can see that the cost of installing traditional power stations, or the cost of kind of new capacity of power stations of coal, nuclear, gas and hydro basically hasn't changed from 2010 to 2018. But for renewables, and particularly for solar, it's got a lot cheaper. It is now 20%. So solar photovoltaics are 20% of the price they were a decade ago, and continuing to fall. And so, you know, anything that gets 80% cheaper is going to see a large rise in demand. And that's exactly what we've seen. A lot of it coming from Asia Pacific, so China and other countries. But there is, you know, there's been an increase in every region across the globe. So there is a lot of solar panels being installed. But what happens if we look at just the UK and just the domestic installation? And I'm going to split it into a number of sections. The first one is just how much of our energy needs does it meet? And I just went onto a website, Energy Guide. I looked at a few of them, and they gave us sort of similar figures for domestic installation of solar panels, where you can get a 1 to 4 kilowatt system. So this is the maximum power that could be theoretically produced by that solar panel. And they did say that 4 kilowatt isn't that unusual. That's probably one of the more common installations. So I took that to be our metric. Now, obviously, it's not going to produce 4 kilowatts every hour of the day. At nighttime, when it's cloudy, and when the sun's just not directly above the solar panel in the sky, it's going to be producing less or zero. So the actual energy we get out every year is a little over 3,000 kilowatt hours. So if we times that energy by the number of households in the UK, which the Office for National Statistics, ONS, says is 28.1, we get 89 terawatt hours. So that is the energy in our little hypothetical scenario that comes from solar panels stuck on people's houses. Just as an order of magnitude thing, if we were to do that and we times this £6,500 installation cost by the number of homes, we're up at £182 billion, which is an incredibly large number. It wouldn't be that figure, partly because if you're buying that many, economies of scale would reduce the per unit price, but also installation cost would increase because there just wouldn't be the number of skilled laborers. It would completely change what the grid would look like. So just to say, it's a rather ridiculous figure and not the way that I think the power system will develop, certainly not the only direction. But what I wanted to do next is take this 89 terawatt hours and put it into context. How much energy are we talking about? And the UK government have this fantastic chart, which is how does energy flow across the UK in a year? So on the left-hand side, you have the generation. On the right-hand side, you have the consumption. And the width, this is called a Sankey diagram, the width of each bar or each flow represents how much energy is there. So this sort of large purple bit at the top is natural gas. A lot of it is flowing into the domestic, so into people's houses for heating, and is used for heating. A lot of petroleum goes into transport. Unsurprisingly, petrol and diesel for vehicles is a large chunk of demand. But what we're looking at is specifically the stuff coming out of power stations. Just as an aside, this 26.2 million tons of oil equivalent, that bit is just conversion losses. That is waste heat that comes out of the power station that needs to be cooled in large cooling towers or in rivers, that actually is not far off the domestic heat demand. So if we could somehow get all of that heat energy into people's houses, we'd have a massive natural gas saving. But that is an aside. That's not what we're looking at here. What we're looking at is this domestic electricity use figure. And that is 9.4 million tons of oil equivalent, which if you convert it to power system units is 11.63, which is 110 terawatt hours roughly. So total domestic electricity use is 110 terawatt hours. Whereas we said in our little simple model, if everyone had a 4 kilowatt solar panel, or every household, that would be 89 terawatt hours. So we're at what? 80% of the domestic electricity use being met if everyone had a 4 kilowatt solar panel. It's quite a lot. But this is sort of taking an average across the whole year. It's also just looking at domestic use. So we said total, these labels have moved. Total domestic energy use is 110, so around here. But our overall total is more like 320 right up here. So that difference is made up of other industries, sort of the industrial and commercial uses of electricity. We can also see the breakdown, gas makes up quite a large percent, wind makes up a fairly large percent. But solar is just this little pink piece here, which is quite small. And we're talking about upping that to be 89 terawatt hours. So sort of up this sort of percentage of that total, which would be 89 out of 320, a quarter-ish, roughly. So a quarter of our electricity needs could be met if everyone had a solar panel. It's probably a bit easier to see if we look at it in this way, where this is rather than a stacked graph, you're just looking at each piece individually. So gas is 40%, wind is 20%, nuclear is 15%, and so on, where solar is down at 4%. And we're talking about upping that to 25. So if we did that, and if there were no other problems, we could get rid of coal and oil and halve our gas usage as the bottom line of how much of our energy demand does it satisfy, or our electrical energy demand does it satisfy. But that's not the whole story. In fact, that's barely any of the story. Do we have the power when we need it? And unsurprisingly, the answer there is no. So what I've done is I've gone to gridwatch.org.uk, which gives you live data of the demand in the UK, the frequency, and where the power is coming from. You can also download historic data. So I downloaded 2019 demand data. And I also went to renewables.ninja, which gives you weather and renewable data. And I modeled, if I had a solar panel on my house of a 4 kilowatt capacity across 2019, what sort of power would that produce? And I can produce graphs like this. So this is the total electricity demand. You can see in the first week of 2019, this is aggregated across the whole country. And you can see the clear day-night cycle. You can see the evening peak, and you can see a sort of more random fluctuation. Let's have a look at whether the solar generation sort of matches up with that shape. And it kind of does. You've certainly got the day-night cycle, although being the first week of 2019, we're midwinter. The sunlight period is pretty short. We've got 2 days where the sun, I guess, wasn't reaching the panels. Maybe it was probably a cloudy day. And despite it being able to produce 4 kilowatts, the maximum it actually did on this midwinter week was 1.2 kilowatts. So we're really, if you sum up this graph, we're really not producing enough. And it's not quite occurring when we need it to. Those peaks don't occur in the middle of the day. I think what's worth doing now is just going to a more detailed model. So rather than taking real historic data, this one builds up what's called a probabilistic model. It takes the probabilities of certain things happening, like certain weather events and weather forecasts and demand uses, and simulates them. So this is one house based in Manchester in the first week of 2019. And again, there's the solar panel switches on and off for quite a short period of time because that's when the sun's up, and you can see that sort of envelope of it gradually ramping up and down. In winter, that would be in summer, that would be a much broader time for generation. And there's also cloud cover for most of the sort of first half of that generation. And that's fairly typical of what you'd see over one house. In terms of the demand, here, because it's one house, you can see individual components turning on and off. I'm guessing this is probably something like the compressor pump of a refrigerator that just comes on every now and again. There's a few devices turned on in the afternoon, but the big spike is where people get home from work, turn on all the devices because it's cold and dark and they've just come home. And and that runs to sort of 10, 11 o'clock for this household. So if we subtract those two from each other, or combine the two of them, that house generates electricity in the middle of the day from the solar panels because there wasn't much demand. And then it consumes energy in that evening peak period. And that's generally what we'll see. This is something that could be smoothed out with batteries, although if you add up all of the power, because this is winter, because it wasn't a sunny day for the full day, it's only generating about 2/3 of the energy it needs, of that house needs through the day. So while you could take that generation, stick it in a battery local to the house, and use some of that power there, it would have to import from the grid as well. If we simulate 20 households, the problem just gets a bit bigger. At nighttime, not a lot happens, but there is some demand. In the day, that group of 20 houses does generate overall. So there's power flowing out of those houses on net, but the big peak comes in the evening. And this is just what happens in winter, where in summer you'd get a slightly different shape. If we sort of take a step back and look across a month of solar generation, you do get a few days of reasonable generation, but they're quite short periods. And there's quite a lot of days of low generation, of just, there was cloud cover, there was bad weather that meant the solar panel wasn't generating what it could. Whereas in the winter, our demand is not going to be affected by, well, it actually is slightly affected by the weather, but not in a way that helps us. And so trying to think of, are we going to meet our demand? Well, clearly not, because even if we were over generating on these days, which we might be actually, it's not like we could store that energy and use it on one of the quieter days, on the days where we weren't generating, because it's so expensive to store energy for such a long period of time. And then just one further look across the entire year, that January period, and in fact the December period, the two ends of the year, unsurprisingly, have quite low solar generation. Most of that generation occurs when the sun's up for a longer period of time. Although even then there are cloudy days. So although I said a household could on average generate 80% of its energy needs if it had a solar panel, that varies a lot. It certainly wouldn't be generating it when you need it. And on the day, on a day-to-day period or within a day, you could certainly get some battery storage that would shift that demand, but it wouldn't be economically feasible to shift all of that excess generation from the summer to the winter. That storage just wouldn't work, or wouldn't financially work, I guess. The other thing to say about this is, in the UK, our highest demand is at the winter. That's, it's dark and cold and we switch more devices on. And in the summer, there's less energy use. So when the solar power is the lowest is when we need it most, I think is the sort of sum total there. And across the seasons, we can't really solve it. Now, this paper was trying to look across Europe at how much, this is the capacity factor, so of the installed capacity, how much power do we actually generate across the months. Nice thing about this paper, it actually said wind follows the demand across the seasons a lot better than solar. And if you combine them in the right way, you can kind of produce what we want. But that's not quite what we're looking for here. So that was part 2. Yes, we can generate quite a lot of energy with solar panels on people's houses, but it won't occur where we need it. And there's other problems about this. So this is what's called the duck curve. I've taken this graph from a newspaper article from Vox. And I think this is California data. So what they've said is, if you get more solar panels, it's going to look like the houses are demanding a lot less energy because they're They're generating it locally through the solar panels. And that produces this belly of the duck. This is meant to be the head, neck, and body and tail. And as you get that dip, you get what's called overgeneration risk. And then this sharp ramp causes separate problems. So the belly of the dip, the problems there are the fact that we've got nuclear, which we don't touch. Its power output doesn't change, partly because it takes it's a slow process to change nuclear power. And in the UK, our power stations aren't really designed for, our nuclear power stations aren't designed to change output like that. We'd also have wind power generating, possibly quite a lot of it. We'd also add on gas power that we need to just keep idling. So this is for ancillary services. You want a lot of power stations running not at their max capacity, just ticking over, as you would with a car. If you just left it running, it's a lot quicker to move to start from a car just running and ticking over rather than one that's not running at all. And if you add all those up, you might actually be generating more than the low demand. And that's a problem. If you're generating more than there is demand, your system frequency is going to increase. And if it increases too much, there's going to be damage to components. So you'd have to disconnect something. You'd probably disconnect the wind because you need the rest of the stuff, which is a real environmental waste because it's sort of, zero carbon energy once you've kind of taken into account the installation costs. So the other side of this problem is this ramp rate. You need to be able to increase power really quickly when those solar panels turn off because it's dark and everyone comes home and turns their lights on and the demand spikes. So it's both difficult to control and you need a lot of total power that you can switch on quickly. So that requires very flexible generation, which you're not going to get from wind because you can't control it. Well, you could tell the wind to not generate, and then you could turn it on and hope that it's there, or forecast that it's there and have a probabilistic measure. But ideally, you'd want something like a combined cycle gas turbine with a rapid ramp rate that allows you to meet that demand, but it still increases the control problem. So that's part two. Part three is inertia and rate of change of frequency. So this is the sort of dynamic effects. The frequency of the power system should be at its nominal, so either 50 or 60 hertz for most power systems. But it will continuously vary because it is inherently linked, like physically linked to the balance between generation and demand. If anyone connects any extra device, the system frequency will decrease. Any, fluctuation in increase in generation would cause the system frequency to increase, and vice versa. So this frequency is constantly varying, and there are various control systems, either automatic or manual, in place to try and keep it within quite a tight envelope of acceptable frequencies. If it falls outside of that frequency, components will start disconnecting, either automatically or through manual action, or components will be damaged. Now, that's sort of what happens regardless of what's connected. But if we have this system here with a traditional, let's say, oil-powered station, got chemical energy coming in, being burnt, heating up water, that steam goes into kinetic energy that spins around a large rotating mass, the turbine. It's a large chunk of metal. And that spinning spins kind of the rotor of that generator to generate electricity at whatever frequency that thing happens to be spinning at. And there will be various control systems in here to ensure that that frequency is held to the system frequency. That then gets sent down a wire and used to do whatever, turn on lights, heat up something, power your computer, whatever it is. Problem is, as I said, anyone connects an additional load, you turn on your light, we're pulling more electrical energy. So we're increasing the current draw, which is pulling kinetic energy out, and pulling kinetic energy out slows that turbine down. And it slows it relative to the amount of rotating mass there physically is. So that's why I say not only is it linked to, is the frequency linked to the generation load balance, but the rate of change of frequency, how quickly that frequency will change, is related to the total system inertia, modeled by, the amount of energy, kinetic energy stored in those turbines. So what all that means is if you have less spinning mass, a less synchronous generation, and more solar generation, which doesn't have these spinning masses, your system frequency is going to change a lot more rapidly. And that's going to be harder to keep between these rather tight limits and control. And if you didn't follow that description, by the way, we spent on the actual course a much longer time going over this in more detail. But I thought rate of change of frequency and the inertia effects or low inertia power systems are such an important part that I just wanted to throw it in there as it will be harder to manage the frequency if you have a system that does not have a large percentage of synchronous generation. And one of the next parts is quality of supply. So ideally, we want our voltage to be a nice, clear sine wave. Our solar panels don't produce that. They produce DC power. So they're going to need to be connected to an inverter. That simple inverters could just say, well, I'll use my DC power, my DC output for half the cycle, and then negative DC output. And if you squint a bit, it sort of looks like a sine wave. There's going to be a lot of high frequency kind of harmonic components here. Better inverters can come up with something that more closely matches the sine wave, but they won't be ideal. And so you might end up with something that varies a bit more like this. And these harmonics, these higher frequency components or variations in waveform shape, they're going to lead to eddy currents, which will lead to heating, or they're going to lead to extra stresses, rotational stresses on rotating machines. They're going to increase the mean time to, decrease the mean time to failure on components. They lead to damage and then lead to problems if they're too great. They won't necessarily be, and it depends on what type of inverters are connected and what the rest of the control system of the power system looks like and what the other devices are and the damping that's kind of on the network, but it's an additional complexity. I think on to our final section, which is faults and distribution. So far we've sort of looked at nothing's gone wrong with the system and we're just treating it as one whole piece of when do we need the power. But realistically, power is used at a particular point and has to flow down wires to get there. So this is a model of a distribution, a simple part of a distribution network. On the left here, that's sort of the connection to the transmission system. And then you've got two lines where at various points, the various bus bars, you'll have a whole load of houses connected. Now, if those houses don't have solar panels on them, all the generation is going to come from the high voltage network and feed through this MV feeder, and the voltage is going to drop as it goes down, and power flow is going to be in a nice predictable direction. If everyone's got solar panels, as we saw in the previous graphs, at certain times of the day, power is going to be flowing the opposite direction, or it might be flowing in the opposite direction. In fact, you don't really know as much about what your power system is going to do in advance. It just becomes a harder problem, both for sort of setting up your power system protections, but also for safety and knowledge of what's going on within your substations. You might also get a voltage profile that's unacceptable coming down through this system, or you might get power flows that are, I guess just on net, the distribution system is going to look a lot different if you're having a lot of distributed generation, and it's going to require operating in a slightly different way. Another thing I wanted to say on this slide, actually, all of the solar panels connected at these buses, they will be responding to the system frequency. So let's say there was some fault on the transmission system that put the system frequency out of range for these components, for the solar panels. They'd all suddenly disconnect at once, which would make whatever problem was happening at the transmission system so much worse, because there would suddenly be a massive increase in demand. And this isn't a theoretical problem. This happened in the UK and has happened in other countries as well, where the ability to ride through faults isn't what it should be. And because the system operator doesn't really see what's going on, or how the solar panels are configured on each house, because they're behind the meter, the meter that's on each house, and not monitored, it's an additional area of risk. So in summary, a 4 kilowatt solar panel could meet most of a household electricity need, other than their car and heating, but generally not when they need it. You could store to balance across a day, but certainly not across the seasons, which is part of what's needed. Nationally, we could have problems with overgeneration and rapid ramp rates, which can be overcome, but might curtail wind power, which would be additional cost and additional environmental kind of CO2 emissions. Lower inertia means harder to control frequency. We might have fault ride-through issues or correlated failure issues. The distribution system becomes more complicated with reverse flows and more complicated power system protection. And we may or may not see power quality issues if we did this. So that's sort of a whistle-stop tour of some of the issues. We do actually have, so on the MSc, we have units on power flow, we have units on power system protection, we have dynamics and quality of supply, which would look at those aspects. We have power system operation, which looks at the generation sort of through the day and through the year. We have sustainable energy systems, which look at active network management on distribution systems. We also have sustainable innovations as well. So each of those units focus on a different aspect and really dig into detail, not just from the solar panel issue, but just in general. So I wanted to just tie it back to the course. And rather than leave everything on a negative, I wanted to just leave an idea with you. There are about 40 million vehicles in the UK with a battery capacity of about, 40 million vehicles in the UK. If all of those became electric, which in the future the UK has plans to have zero tailpipe emissions, that would give an energy stored in the batteries per vehicle of about 62 kilowatt hours. So 60 times 40 would be 2.4 terawatt hours stored in batteries sitting in vehicles all around the UK. And given that our total electricity demand in the UK was 324 terawatt hours, that gives a daily average of about 1 terawatt hour. So we've got this huge energy. Okay, those cars will demand a lot of energy to be recharged every day, but it's also a huge balancing potential. I said we couldn't store that much energy, but if we've got 2.3 terawatt hours stored and our daily average is only, like our total average is only 1 terawatt hour, only a fraction of that would be needed for storage and moving things around. So it's a huge potential as well. And I think I wanted to finish there. If anyone has any questions, feel free to, I can see some in the chat already. So
yeah, I think we do have a few questions in the Q&A. Just put, so so we've got a question from Mike.
Yeah.
So I'll just read it out for the rest of the viewers. So Mike says he's previously explored vehicle to grid technology, just what you mentioned there, James, to counteract availability of renewable energy such as solar and wind. Would the course provide opportunity to review this?
Yeah. Okay. So there is nothing in the teaching material specifically on vehicle to grid. That said, there are the final unit, Unit 8, which is sustainable innovations. I think that would be a really sensible topic. You can choose your own topic for that one, or it's a group project. Equally, that's something you could choose as a topic for the dissertation. And I know people with researchers within the department have looked into vehicle to grid. And we've had other master's dissertation projects on vehicle to grid. So nothing explicitly taught in the talk material, but it's certainly something you could choose as one of your projects.
And we also have a question from somebody from the NGO London Green Bridge. Oh, right. Okay. So asking about online courses available. Yeah, I mean, absolutely. That's something we could look into. If you would like to email me at studyonline@manchester.ac.uk. That's at the bottom of the presentation slides there. We can certainly look at get back to you on that one.
I can see another one come in from Tamor Gill. Do we have enough distribution and transmission system so that renewable energy can be added? So, okay, does the UK? I think the big thing here is it depends. So I'm working with I'm one of the master's students who's on the electrical power systems MSc at the moment, works for the UK system operator, looking at one of the existing kind of constrained boundaries where often we're at the limits of the power transmission in the UK. And they're saying, well, rather than upgrade the lines, rather than change the actual physical assets, can we do something smarter about controlling the system? Can we look at either adding something like StatCom, SVC, or SyncComp, so some sort of power electronics device, or can we? So that's one project. I've got another MSc project who's looking at controlling distributed generation locally around that constraint boundary. So possibly we don't need to upgrade much if we had a lot of local generation and local storage, and we were able to manage transmission boundaries a lot smarter than we currently do, and we move into things like dynamic line rating, then there may not need to be very much upgrades. If we want to have large offshore wind power in Scotland and want to continue sending that power down the backbone of the UK without kind of the other pieces, then definitely not. So it depends is a frustrating answer, but that is the correct one for this. Okay, another one. Does the course deal with battery energy storage systems and green hydro contribution? Again, we don't explicitly teach anything with battery storage systems. We do have a power electronics, machines and drives research group within the electrical engineering department that do research these things, but they're looking at more device level stuff, whereas this course is more about interconnected systems. So nothing explicitly, but again, we've had people look at battery energy storage as part of master's projects. So once you go through the taught element, you could pick that as a project. Okay, Gilbert saying, after the program, can I proceed for a PhD? How can I have a hand in the projects? Okay, so after any master's, you could proceed to a PhD. In fact, you can go to a PhD without a master's. I didn't do a master's myself. I went straight from my bachelor's to a PhD. That's not the challenge. The challenge is finding a supervisor and finding funding. And those are quite a linked problem. So having a good grade in a very well respected master's is a very useful stepping stone and makes it a lot easier to get into a PhD program, particularly if your dissertation was a very high quality and in the area that you wanted to move into for your PhD. So it's certainly something that can help a lot. I also know that some people have come out of their MSc and then continued working with that same supervisor to go on to do a PhD. It's sort of that opportunity to, because they already know you, because they've already worked with you on a similar project, sort of staying on it is sometimes possible. But that's a bit of a luck of the draw thing. It depends on whether the supervisor has capacity, whether they have funding, whether they kind of want to take on another person. Daniel says, do you think the option of tidal energy as a predictable source could help balance the grid frequency? Not my area of expertise, and I say that because I know in the Tyndall Centre we have, Tyndall Centre is another research group. The University of Manchester has quite a large number of researchers working on different aspects of sustainable energy, power systems, renewable power, power electronic devices. So the Tyndall Centre has a few researchers looking at tidal energy. And I don't know what their conclusion would be. My guess is we don't really know what to do. There's a lot of energy there, but I don't think people have harnessed it in a very cost-effective way at the moment, although there's still lots of research going on. You certainly have the countries globally that have the highest renewable sort of percentage of their energy that's coming from renewables. Almost all of them are from very large hydropower schemes where you can just dam an entire valley and then fill that with water, and you can just take the water out whenever you want. So balancing is easy. You just open the floodgates as much as is needed to match your demand. Okay. This kind of power has been introduced into Malawi, but somehow not reliable as we lose power frequently. Yeah. Again, we have some students. There's a couple of students from Uganda who've been looking into system reliability and system balancing, where you do have a lower reliability than somewhere like the UK. There are a lot of things that can cause low reliability, and there's questions over kind of where the faults lie, whether it is kind of an inadequacy issue, as in you don't have enough generation, or whether there isn't enough active network management at the distribution system to be able to reconfigure the network when there are faults. There's not enough resilience within the network. And again, we have a couple of researchers who specifically work on resilience as their research area. So yeah, I don't know Malawi specifically, but I know that power system resilience is something that some of the researchers at Manchester have been looking into. And sorry, Mike, I realized you were probably one of the first ones to ask the question. And I'm just going to skim through it because it's a rather long question. I work for a consultancy, building services. Yeah, okay. Will the course benefit me working in the building services industry? This is a really good question because it's something we get asked quite a lot. And again, the course overall mostly does look at national power systems, sort of transmission and distribution level. But the fundamentals of power flowing through around a network are the same at whatever voltage you're running at. And the protection systems are going to be similar. Not the same, but the principles and the things you'll learn around that will be applicable. Some of the analysis methods will be very applicable. So things like the dynamics and quality of supply, things like power system protection, Maybe something like power system plant would be less relevant. And certainly the examples will be more taken from power systems on the sort of transmission and distribution level. We do have, in terms of the existing kind of profile of students, there's been some that have come from building services, although it's not direct, it's not, as you say, it's not fully relevant, but it depends what you do. So if you're working for large data centers, if you're kind of involved with your distribution networks in working on the sort of the local substations and liaising quite heavily there, and you're one of those engineers, that is a lot more relevant. That's very relevant. So whereas if you're a Sparky kind of connecting up offices, then no, not relevant, or not nearly as relevant. So I think the best way to work out kind of the suitability is to get in touch with us on the study online at Manchester. And if one of the study advisors like James can't help, then it can always be forwarded to me and I can have a chat with you. Is the Masters accredited? Great question. Yes, it is. It's accredited for further learning with the IET as part of the CEng status. So yeah, we've got our IET accreditation. Do we have any subjects on smart grids or blockchains in smart grids? Yeah, okay, so we have an entire unit on smart grids and sustainable energy systems. You could do an entire MSc on smart grids. Smart grids means so many different things to different people. And, you know, smart grids, there are people who just look into the communication aspects and are communication engineers rather than power system engineers. We don't do a massive amount on that bit because, you know, this is mainly targeted towards power systems. But in terms of what are smart grids, what are the active network management techniques that are relevant to them, how do we manage the energy trilemma between reliability, cost, and CO2 emissions, that's definitely, there's an entire unit on that. Am I eligible for this program as journeyman for power lines? Best way to answer the question of am I eligible is just to get in touch with us and send your CV across. For kind of minimum requirements where I think it's worthwhile, if you've got a relevant degree, so you know, something where you've done engineering maths, is now because there is some quite heavy maths involved, particularly in the sort of dynamics and quality of supply, some of the economic analysis, some of the, yeah, there's quite a few places where you need sort of strong maths. That's something I look out for quite a lot. And you'll need to have some experience within the power system kind of and circuit analysis. But yeah, the best way to find out is to send your CV across and ask the question, and we can get back to you on that. Recommended prior reading to commence the course. Oh, okay, yeah. Depends what area you want your weakest on, would be my recommendation. So the course textbook that we use mainly in Unit 1 is Granger and Stevenson's Power System Analysis, I think it's called, but it's known as Granger and Stevenson. That one we actually go through in Unit 1, so maybe that's less relevant. It might be worth brushing up on your mathematics, because that's not something we teach, it's just something we use, particularly if you haven't studied maths for a while, as is often the case. I mean, I have designed Unit 1 to be a more gentle introduction and a refresher of undergraduate material. But maybe something like Stroud's engineering maths would be good. Maybe refresh some circuit analysis, AC power kind of stuff. So Nielsen and Riedel's electric circuits, if that's your weaker area, or if you've got an electrical degree but you haven't done that much in the power system sector and you want a more conceptual overview, I really like, have I got it with me? No, I don't. Von Meyer's Electrical Power Systems, A Conceptual Introduction, which is a very readable, doesn't read like a textbook at all, and just gives you a good overview of a load of different kind of aspects. Okay, and we got another question. As a power electronics expert, what's my recommended focus area in smart grids? As a non-power electronics expert, I'd say I don't know. I know that, again, in the devices, the power electronic and power devices group, we have quite a lot of people looking at that, where they're looking at the use of HVDC and multi-point HVDC as the sort of future of not just interconnections, but bulk power transfer and connections to renewables. And I think the control aspects of more complicated HVDC networks would be a really interesting area for me. Although, again, I'd want to talk to my colleagues who actually work in power electronics to get their view. Okay, I'll be using a work computer. Is there a list of software that will be required? Yes, and if you email us, we can send you that list. And someone else has asked about software. So the 4 bits of software we use at the moment, although we occasionally change them, are MATLAB, PSCAD, IPSA, and PowerWorld. All of those bits of software are supplied by us, or we use the free version or student version, or provide access to you. IPSA, I know, only runs on a Windows computer, and you do need admin rights to be able to install it. Although for some of those, I think you can probably VPN, like virtual private network and remote desktop, into one of the university computers. Although maybe don't quote me on that because I can't remember. But yeah, those are the 4 bits of software: MATLAB, IPSA, PSCAD, and PowerWorld.
Excellent.
Right. I can see there's also some questions in the chat. It's great. There's been so much coming through.
Yeah, there is.
I got a question regarding frequency changing. Yeah, okay. So this is a frequency response. When the frequency changes, what do you do? This is covered in about 2 or 3 weeks in Unit 2 of the MSc. I will give you a very inefficient but quick overview. Firstly, inertia will resist the change in frequency. So hopefully you've got a large inertia on the system and your frequency doesn't change too much. Then some generators will be assigned to be grid following. They'll notice that change in frequency and open and close valves to increase or decrease the power of that generator to hopefully stop the change in frequency. Then there will be secondary and tertiary actions, maybe some of which are automatic, maybe some of which are manual, where a system operator can go in and say, okay, we need to bring the frequency now back to nominal. What are we going to do? What are we going to change? So there is a whole mix of things that happen, some of which are sort of control systems within certain power plants, some of which are national control, some of which are intertrips and automatic changes, some of which are system operator kind of manual action. And I'm seeing that you're moving, James, you're moving ahead, so I probably have reached the end of my time for questions.
No, that's great. Thank you, James. That's really excellent information, and thank you for answering all those questions. Some really interesting ones there, and a lot about the course as well. So it's good to see that there's a lot of interest in expanding into the course and learning more about these topics. yeah, there's a little bit more information here about our MSc in Sustainable Electrical Power Systems Engineering. Just a brief overview of the logistics and the details. So approximate workload for the program is 15 hours per week, and depending on what stream you're on, the program will take between 12 and 30 months to complete online. So the online setup of this program provides a very flexible learning environment for all students on this, and you can fit it around your employment or other commitments. And there's a lot of applicable practical nature to the program which you can apply to your workplace, especially in the dissertation project, which we've mentioned a couple of examples of some students' dissertations today. And so, yeah, there's definitely lots of practical elements that can be applied to employment and future career progression. As mentioned before, the program is accredited by the IET, and our next enrolment is in February 2023. So if you are interested in applying for the program, you can visit our program webpage, which you can find if you just Google Sustainable Electrical Power Systems Engineering, you'll be able to find it there, or you can use this link on the slide here, manchester.ac.uk/power systems. That'll take you to our program webpage, lots more information about the program, and you can follow the links there to apply. And also, please do get in touch. You know, we have the email address here, studyonline@manchester.ac.uk. So if you have any further questions about the program, I will be able to help you answer those, and James as well. I'm sure we'll be able to answer some more of the technical ones about the program. So yeah, get in touch. We're always happy to talk. And I'm just going to send a quick poll out to all of our attendees. So there's just 2 questions to answer, and it's just yes or no, really easy to answer that. And what we can do is, if you would like, we can set up a consultation to talk more about the program, a one-on-one phone consultation. So if you get in touch with me, we can arrange that for you, and I can answer any further questions you have about the program.
Just while people are doing that, I saw another couple of questions come through. One is there going to be a recording available? So James, I'll leave that to you to answer.
Yes, there is. This webinar will be posted on our YouTube channel, and I will send out emails to all our attendees today with information about how to access that and how to view the webinars. We've also got lots of previous webinar content on there. So if you want to look now, you could just go to YouTube and search Study Online Manchester, and there's lots of content there for you to look at. But I'll send an email over with the specific details about that as well.
Yeah, and there was one more in terms of scholarships for the course, so I'll answer that. The university does have a small number of scholarships, although they're only under quite specific criteria. I think the best way, you can search on the university website to find the scholarships that are available there, and I'm sure if you got in contact with us, we'd be able to point you to the right website. But yeah, sadly there's not as many of them as I'd like, but there are a few.
Yes, thank you, James. Great. Okay, well, thank you very much for all that really useful information, James, answering all those questions. And thank you everyone who attended today. It's been great to get to know a little bit about everyone's backgrounds, and there's already lots of people thinking about the applications of this program in various workplaces. So that's really nice to see. And yeah, we welcome any more questions or conversations you want to have about the program. Just get in touch with me at studyonline@manchester.ac.uk. But thank you for attending, and we'll finish there, and we'll speak soon.
Thank you, everyone.